Today we are presenting Addism, which is a modular game engine agnostic framework and primarily used for 3D drone path planning and simulation. So to introduce our project and why we felt motivated to pursue it is that we see many challenges to the development of motion planning algorithms. First, they're fairly computationally expensive and complex to develop and test these algorithms. As well, real-world testing requires costly equipment and extensive sensor suites. We've seen in the past that simulators provide a way to reduce costs and control the environment. When we think back to the sensor suites, this reduces the load on teams to actually have the physical sensors. And when they're doing preliminary testing, they can use digital ones in a simulator. Ground-based simulators are fairly common, but air-based simulators are less accessible and less modular than their ground-based counterparts. We do see that there are a few air-based simulators, but overall they have limited flexibility as well as a seemingly large overhead and large learning curve to pick them up, which is why we're presenting a more accessible and iterative solution. So we see some of the related works. We have AirSim, which was developed by Microsoft and leverages Unreal Engine. Here they focus on real-time simulation and integration, primarily with machine learning frameworks. However, there are some limitations that we've studied with AirSim, being that it is tightly coupled with Unreal Engine, sort of restricting the flexibility of the platforms, as well fairly extensive computational demands, and it lacks support for iterative pre-planning and pathfinding, which is what our project really strives in doing well. As well, there's Gazebo, which is an open source simulator that is based on the Open Dynamics engine for rigid body dynamics. And this supports various sensor suites as well, making it versatile for robotics validation. However, with Gazebo, it has a fairly steep learning curve and is very Linux-centric, as well as with complex and dynamic environments, it can face performance issues. So our solution here is Adasim, which will utilize Unity to create scenes and run scripts.
Continuing on where Cole left, so we present our solution as AdaSim, essentially adaptive simulator. While he mentioned about the issues we faced with previous works where it was tightly coupled with one particular game engine, and moreover, they supported more more real-time scenarios compared to pre-planning scenarios that we usually see. And other solutions usually had like 2D components rather than 3D. So that was the main motivation to have something that is decoupled enough that you can use any sort of game engine to run and simulate your environment. At the same time, you have another library that keeps all the algorithms. So MPlanner library does that. We have a planner class, which is the base class which does that. I will now share the screen to just give a brief overview about the code base. All right. So essentially we have three components here. The first component is the environment component that you see here. We essentially convert the representation that you have from a particular game engine. You take that, all the information about the environment, obstacle, start and endpoint and everything, and you want to encapsulate in a grid format, and which we use as a grid class, which does that. And we read it through a JSON file, which the Unity engine, which we particularly use as an example here, uses that. And once you have that JSON file, you ingest it into the library and this environment file. Where using that, we create a 3D grid where each grid represents the part that the robot can take. You also fill the grid with the obstacles and everything to essentially simulate the environment, and then you essentially run your algorithm. So this is the main part where you have a bunch of options where you can calculate the cost to move to the next neighbor, which direction you need to move. And you also have support for like multi-world scenario. Essentially, you connect a bunch of grids and you essentially make a world and you can transfer between different worlds. So we also have that feature. And once the whole Unity or Unreal, whatever game engine you use, you have that environment in the Python 3D grid, you can go to the planner class and implement your desired algorithm. We have some sort of base classes that one can use. We have this distance heuristic, which is the main heuristic you sort of use to judge whether you have to take path A or path B. Evaluate neighborhood gives you the exact values, and based on that, you can use use the distance heuristics, get neighboring nodes, give you the list of possible nodes, and based on that, you get your path planned node. So these are a bunch of base functions which you need to implement. One of the examples that we provide in the library is A star, which sort of implements all these base class, and essentially in the end, you just have to call one function. A good example we have is here where based on the environmental bounds, you set it based on the coordinates that you get from JSON file. You essentially give the coordinates for obstacles, and once you have that, you create your grid matrix here with start and end position. And once you have that, you call the algorithm and just get the plant path. And essentially, once you have got the plant path, you can get exact waypoints, which feeds to the Unity. Another neat feature is that essentially you have this whole decoupled library where you give like all those real-time continuous inputs, and at the same time you can get the same output, and you just need to feed it back to the Unity. So I think this is a very neat feature, and essentially we have solved the big issue that we had, like each sort of simulator was attending one particular game engine, when we have sort of decoupled that. And we have also allowed a good enough library that you can implement multiple algorithms and you can rapidly test them. So moving on, we'll take over and we'll give you through the demo how to set up everything and show you demo with a simple environment as well as a city environment, which we get from Unity.
Hello everyone, my name is Will Stonebridge, and I'm going to be giving a demo of our project, starting with this very simple example we have here, and later moving on to a more complex example. So in order for our asset to work in a Unity project, we need three things. So the first thing is a boundary, which basically restricts the area that a robot can move in. So for us, it's this green box here. It's just the box labeled boundary. And as you can see, I've restricted it so that the robot cannot move above the boxes defining this maze. The two other objects are a goal, which is just any Unity object. In this case, it's a sphere, which is named goal. And last but not least, we also have a robot game object, which again can be any Unity game object, as long as it's named robots. And it has the attribute execute pathfinding script, which we've provided in our Unity asset, as you can see here. Now, in order to basically simulate whatever motion planning algorithm you're using, all you have to do is hit run. In this case, we're using Dijkstra's, but if you wanted to implement your own, you just have to follow the steps that Naman laid out earlier. All right, and as it runs, I'm going to point out a few things. First is that we've basically marked the path so that debugging is easier. I'm also going to point out that the robot has chosen a path that doesn't directly hug the wall, even though that'd be easier. And this is because of the object growth algorithm that we talk about in the paper. All right, we're now going to move to a slightly more complex scene. So this low poly city is actually something we got off the Unity store, and we're using it for two reasons. The first is to demonstrate that our asset works on even more complex scenes like this one. And also we want to demonstrate that our asset can be readily applied to basically any existing Unity project. So in this example, we have this drone at the bottom here, which is going to try to make its way to the yellow taxi. And we're actually going to do this with two algorithms. So right now we have Dijkstra's running, which is going to take slightly longer to compute a path than our other example, A star. However, it will deliver us a shorter path. All right, and now that it's computed and it's following the path, which seems pretty reasonable, I'm going to point out that in the bottom here, we've gotten some statistics. So the path is 74.9 feet long, and it took 5.9 seconds to compute it. All right, we've now moved on to A star. And as you can see, the path is slightly different. It looks like it's moving a little bit more to the left and it's dipping down a bit quicker. However, it's still getting to that yellow taxi. And also looking at the statistics, we can see that it's about 3.7 feet longer. However, it only took 4.9 seconds to compute, which is about a second quicker than Dijkstra's. As this example demonstrates, we think that AdaSim provides an easy to pick up and adaptable framework for developers to test their robotic motion algorithms. Thank you for watching.